IESWA section chapter of 2022 technical webinar. Today we have Dr. Sumaya Mahmoudzadeh with us. Thank you for accepting the invitation. I leave Dr. Sumaya will introduce herself, but I'm going very quick through the IES chapter for this year. I would like to have this opportunity to thank the previous past chair, Dr. Amir, that he's done a really outstanding work over 2022. And that had led to several activities and awards. We had last year 9 technical activities and 3 social activities, including dinner, mid-year, and end of year with some of them 40 participants. Last year we received the IES Best Chapter Award, and also we received the Most Active Chapter Award from the IEEE Western Australia section for demonstrating the high membership growth. This year, the executive committee, it consists of the chair would be Dr. Adnan Hayat, which unfortunately we don't have him between us now. He's in overseas. The vice chair, it's me, Moyed Mokbel. The secretary is Dr. Hai Wang, the treasurer Mr. Member Samu, and the industrial chair, Dr. Shoaib Asadul-Zaman. Thank you for everyone for attending this webinar. I leave it to Dr. Sumaya to introduce herself and to start the presentation. I think it's all in you.
Thank you very much. Right. Can you see my screen?
Yes.
Great. Good afternoon. Thank you very much for having me today. I'm Sumaya Mahmoudzadeh, currently working as a lecturer at Deakin University and acting as a team member of course leadership for Bachelor of AI. I'm also academic chair and campus coordinator of 3 main AI units. And about me, so I did my PhD in computer science with the focus on AI, robotics, and autonomous systems at Flinders University. And then I started my first job as a research fellow at Monash University. In 2018, I joined Deakin, and now it is 3 years that I've been working here. So my research expertise includes artificial intelligence and machine learning, focusing on autonomous systems and unmanned vehicles, particularly on the water, surface, and aerial vehicles, with practical applications in oceanography, environmental monitoring and protection, and also smart agriculture. This was a brief story about me, and today I will talk about multi-agent cooperative mission and motion planning, and we'll dive in depth of its challenges and advances. So, yeah, advances in hardware technology, in fact, facilitated integration of sophisticated software and also augmented the onboard intelligence for unmanned vehicles. As a result, they can operate in complex missions where continuous transformation in environmental condition calls for a higher level of situational responsiveness and also autonomous decision making. There are different classes of unmanned vehicles for aerial, underwater, surface, and ground operations. Each of these vehicles has different properties, different hardware maneuvering capability, and different applications. For example, the most sophisticated quadrotor can fly maximum of 40 minutes in ideal situation, while this duration is between 1 to 8 hours for AUVs, depending on the class of the vehicle, and over 8 hours for the surface vehicles. But the common point among them is that they are all resource-constrained devices, means they have limited battery, limited computational power, and also restricted communication bandwidth. Increasing the level of autonomy allows reducing reliance on human supervisor. Autonomy in real world with unknown events needs adapting the continually changing situations, and this relies on the proper understanding of the surrounding environment. So complicated missions that cannot be accurately defined in advance will need to be resolved through intermittent communication with a human supervisor. And this will kind of restrict the capability and accuracy of such vehicles. A fully autonomous vehicle should have capability to consider its own position as well as its environment to properly react to different sorts of unexpected or dynamic circumstances. This presentation aims to provide a general background of some unmanned vehicles and existing difficulties on the way of having a true autonomy on their applications. We will also discuss about how to assess the levels of autonomy and its related properties in internal and external situational awareness for having a robust motion and mission planning. The present condition of a vehicle and incoming load of surrounding information should be considered simultaneously to form an appropriate mental model of the existing situation. This mental model or this picture, in fact, creates the central organizing pattern from which all decisions and action selections take place. This diagram shows the impact of situational awareness on decision-making process. So situational awareness, or we call it SA as a short name, along these lines incorporates three parts, including observation of the surroundings, comprehension of the events, and projection of plausible events on one step forward or in close future. At the first level of SA, which is the perception, the attributes and dynamics of the environmental factor will be considered or will be perceived. This process will be followed by the second level, where the perceived information will be comprehended through synthesizing the disjoint critical factors and understanding what those factors means in relation to mission to a particular mission tasks. Eventually, the third level involves projecting the next status of the entities in the environment that enable the system to act and respond to the right situation in a timely manner. Well, a mission can be defined as an operation to complete a series of tasks. These tasks can be homogeneous of the same operation or combination of multiple operations. For example, in a case of underwater, a mission can be defined as a set of tasks, including water pollution monitoring or geographical sampling, mosaicing seafloor, offshore installation, underwater navigation, data collection, or other sorts of operations. The tasks can have different order, priority, and completion time. Mission planning for a single vehicle in a large-scale operation has some restrictions, such as higher cost of deployment, limited coverage and operation periods, and so on. So the vehicle, in order to complete a mission, a vehicle should recharge multiple times and deployed to complete all tasks. And this is a time-consuming process that cannot be appropriate for time-critical or urgent operations. In contrast, multi-agent task allocation, or we call it as a short name, we call it MRTA, usually used to perform missions that are time-consuming or difficult to be carried out by a single vehicle. Multi-agent systems are more capable of handling larger scale and complex missions than a single robot system. The MRTA technology aims at maximizing the operational performance through regulating the underlying mission in the context of task allocation or task assignment. Generally, a mission plan has two main objectives. The first one is to increase the individual vehicle's mission performance, means maximizing number of tasks completed by each vehicle and taking the best use of battery lifetime. The second goal is to maximize total operation productivity, means maximizing the use of accumulated operation time to complete mission scenario and optimizing the order and priority of operations. But there are vehicular constraints involved in this process, including battery lifetime, computational power, memory capacity, degree of freedom and maneuverability, connectivity, and also bandwidth restrictions. There are also environmental constraints and challenges such as predictability, complexity, and also uncertainties. In this category, we can name the water, wind, or current disturbances depending on the application, collision boundaries related to moving or static objects, and unknown zones, which are hard to estimate what are they or what is in that zone. Therefore, the most important thing to consider at all stages is that the mission success always tied into the vehicle's safe deployment. Let's talk about AUVs as a complex example. So AUV uses a set of sensors to perceive the surrounding. This includes inertial navigation system like gyroscope, accelerometer, compass, and so on, visionary sensors, temperature and depth pressure sensors, battery and leak sensors, and so on. AUV is one of the complex platforms in robotics domain due to some reasons. The first one is low operational bandwidth. This means the only possible time for them to exchange the data and communicate to the operator is before and after a mission. Another reason is that AUVs do not have access to GPS or internet when diving depth. Cameras can cover a very limited range of meters, and another issue is accuracy of the sensory data due to severity of the environment. In fact, on the water, sensory data are very noisy or uncertain. One approach to deal with sensors' shortcomings is to use signal-level data fusion techniques, which aggregate data from multiple sensors, enhance noisy and uncertain data, estimate and augments the missing data, detects multiple sensors redundancy, and extract the relation among obtained information. In general, data fusion aims at providing optimal estimation of a specific real-world condition using observable and sensory data. For AUV's safe deployment, a path planner is required to deal with the surrounding changes. So for this purpose, besides the vehicle's motion restriction, we need to consider the water current data, because favorable current can be used to accelerate the mission, while the adverse water current should be avoided as it can cause drift to vehicle's motion or can just drift it to an undesirable direction. Another thing to consider is improving the navigation accuracy that entails active obstacle avoidance capability to keep the vehicle's safety margin with the barriers during the deployment. So this includes the estimating the object's dimension, detecting the type of the object, whether it is static, it is dynamic, tracking the object's distance, velocity, and direction, tracking its behavior in one step forward, whether it is moving toward or just deploying. And also, we can say estimating the threat or danger degree. We can just have a kind of label for that. Ultimately, the produced trajectory should also guide the vehicle to return to the charging dock, or we call it docking station, when the battery is low. AUVs should have a certain degree of autonomy to complete the mission, and accurate timing is extremely critical in this process. On the other hand, AUV's failure in underwater missions is not acceptable because they are extremely expensive. For having a successful mission, a decision support system usually incorporates two deliberative and reactive execution layers. One is the mission planner, and another one is the motion planner. So the motion planner takes advantages of the fused data to accommodate situational awareness in dealing with uncertainties, and then provides a reliable trajectory to ensure safe and efficient deployment. On the other hand, the mission planner handles multiple vehicles cooperation and in some cases fault tolerance by ensuring no overlap exists between the fleet's operation, managing the individual and overall operation time, optimal task assignment and route formation, as well as handling the internal or external errors. Here we present, as an example, we present multi-AUV's adaptation to time-varying dynamic water current in different time intervals. So the red circle and the yellow square respectively correspond to the starting and the destination position. These little arrows show the water current direction, and the color map shows the current strength, or we call it magnitude. As you can see here, in the first and the second steps, all four vehicles follow the current direction, meaning that they use current force or ride on the current flow to accelerate their motion and reduce the battery consumption. Accordingly, the same adaptation occurs in the third and the fourth time steps until all vehicles get to the destination point. In this process, the system constantly replans new trajectories to handle new changes in the water current direction and also magnitude to safely guide the vehicle toward the destination. In another example, here we present a path planner's adaptation to the environmental changes in four time intervals, where the uncertain and moving obstacles are also taken into consideration. So this is the initial path generated by the system, incorporating moving or uncertain obstacles. This is according to the existing situation of the environment at the moment. These circles, these white circles, represent the object's collision boundary at each time step. So the yellow and green spots represent the starting and the docking station, respectively. The red circle along the path corresponds to AUV's position along the generator path. So as you can see here, in the second time step, some of the objects have a growing uncertainty, or they are growing in dimension. This means the safety margin for these spots needs to be updated. And some other objects' location is changing, which might be due to the water drift or self-motivated motion. Accordingly, the system replans a new path to tackle the new collision boundaries while adapting the water current direction. The change in this object's status, this one here, is not considered in the replanning process because the vehicle is already past that spot. But it is clear that the new replan trajectory guides the vehicle to safely pass the rest of the objects on its way. The same for the third time step, where another replanning is happening here, and also fourth time step. You can see how the path deformation is happening to deal with these growing uncertainties or moving objects. This is how path planning process actually tries to deal with dynamic and uncertain events in the environment. This is the three-dimensional representation of the system's adaptation to the environmental changes and shows how the generated path tackles the obstacles in depth. So these layers correspond to the gradual changes in water current map in 4 different time intervals that we already presented. And eventually, this is how Path Planner provides a safe deployment for AUVs considering all environmental and vehicular restrictions. Now let's switch to the mission planning process. Here's an example of an actual mission. Due to the unique underwater ecological nature of Australia, one of the challenges of recent years is to eradicate the cuts, or we call it starfish population, that has a destructive impact on the coral in Great Barrier Reef area in Queensland. So the idea is to employ a group of cut spots AUVs, working cooperatively for cuts eradication mission. Cut spots AUVs are equipped with vision-based technology and injection arm to automatically detect and inject the cuts. So tasks in this work are defined as injecting the cuts, where each task associated with a priority rank and completion time, depending on the intensity of the cuts in each spot. So the AUVs are required to constantly find the cuts within the complex reef environment and cooperatively eradicate maximum number of cuts while moving toward the destination. So tasks should be arranged to govern the AUVs to the destination and meet the time restriction as well, which is a joint, discrete and continuous multi-objective problem resembling both knapsack and dynamic TSP. Okay, so situational and cognitive load awareness allows multi-AUV system to identify when cooperation is needed, to share available resources and entire mission reformation when one or more vehicles fails to continue the intended operation. So for solving the cuts eradication problem, we proposed a cooperative fault-tolerant mission planner to accommodate parallel operation and also collective resource sharing and also adaptive replanning for uninterrupted operation in fault occurrence. The proposed system is established upon a hierarchal architecture, including multiple phases to facilitate different stages of a mission. One of the first step or first phase So one of the significant hurdles in multi-vehicles mission planning is to ensure no overlap occurs in the fleet's operation. For pre-mission processing in phase 1, the system incorporates a model of the environment and a number of functioning AUVs to effectively and reasonably divide the operational field into K exclusive partitions, where K refers to the number of the vehicles. So this process will guarantee a conflict-free operation of AUVs without any mission overlap. In phase 2, the first step is to extract the probability of cuts distribution in the operation environment. Obviously, this will be a non-uniform distribution in a 2D volume. So phase 2 incorporates the physical model of the AUV and the information of the segregated environment from phase 1, as well as the position of the distributed cuts in each partition to determine the best processing order of the tasks for each AUV. This process, again, aims to maximize the number of cuts eradication, taking the shortest travel length while managing the operation time simultaneously. In phase 3, given the synchronization condition, if the flag is off, the system will output the optimum route, which was generated in phase 2 for parallel operation of the AUVs, and the process will be iterated until all AUVs batteries are depleted. In contrast, if the synchronization flag is on, the system will adjust its behavior and adaptively replan a new mission scenario that facilitates cooperation of the idle vehicle's residual resources to complete the mission while, again, handling unforeseen faults to ensure uninterrupted operation. So the cooperation and fault-tolerant property of the proposed system guarantees maximum cuts eradication and retains the system performance at a near optimal level by preventing interruption when failure occurs, leading one or more vehicles to abort their mission. The proposed system has the capacity of situational awareness to perform adaptive replanning with respect to the changes in the surrounding environment or internal status of the AUVs. This is the general overview of the operation diagram for the proposed system. So here we developed a new algorithm called heuristic fleet cooperation. HFC, we call it HFC. That is population-based evolutionary approach, particularly designed for solving multi-vehicle dynamic task assignment problem. The HFC is established upon a hierarchal priority evolution and is able to rapidly prototype multiple optimum solutions. This novel cooperative task assignment algorithm uses clustering, ordering, screening, and cooperation operators to address the problem. The detailed mechanism of this algorithm can be found in our published paper, I guess in 2020. So to demonstrate the effectiveness of our designed algorithm in this architecture, HFC is applied to investigate the model's performance in two different operation modes. One is the conflict-free operation, where AUVs have no communication with each other and only concentrate on completing their own assigned partition. This has a benefit, which is preventing duplicated treatment of the treatment to the same spot, which is time-consuming if we redo the same task for multiple times. And then we have the cooperation mode with the same environmental and vehicular setup. As shown in this figure, the affected area or the the affected area is divided into 3 partitions presented by different colors, because we consider 3 AUVs. Zone 1, which is the purple zone, is the most crowded area that comprises 65 CUTS centers, while zone 2 and 3, shown by green and blue colors, correspond to less populated areas with 17 and 18 spots. So this difference is in number of spots in 3 partitions is used to show how integrating cooperation operator enables less loaded AUV to use their extra battery time to assist the overloaded vehicle. So this cooperation enables the AUV to exchange their mission information, communicate with each other, communicate their current battery status, pose, covered area, and the uncovered sections of each partition. Okay, as shown in this figure, the AUV operates, all AUVs operate exclusively on their own allocated zone. This is the conflict-free operation. They don't know what's happening in the other areas because they don't have any communication. As a result, the AUV 2 and 3 can monitor all their allocated fire spots, as their partition is considerably smaller than the first AUV. On the other hand, the first AUV has to compromise on leaving some of the spots unexplored in order to manage its mission time and avoid time violation. In contrast, in the cooperative operation, the capturing pattern of these 3 vehicles shows that AUV 2 and 3 extend their mission to capture some of the unmonitored spots of first AUV, that is presented by these red circles, red dashed circles in this figure. Another performance index to be analyzed is the residual time for all AUVs that should be minimized in order to enhance the operation time usage. The residual time gets a negative value if the operation time is greater than battery time. This means the corresponding AUV experiences time shortage for accomplishing its operation. Comparing these 2 graphs, there is no considerable difference between 2 modes for AUV1 in terms of time management. The reason is that this vehicle is already assigned to the biggest zone, and in either case, it struggles to complete its own tasks, and no extra time is left to help the other vehicles. It is also notable that although the first AUV can manage the operation time to avoid violation, the red threshold that is presented by red dashed color, the convergence happens after 140 iterations, since the first AUV iteratively leaves some spots unmonitored to fit the operation time into defined threshold in both operation modes. Now, on the other hand, as you can see here, the AUV, the second and third AUV can complete the iterations with significant positive residual time in the conflict-free mode, meaning that they do not use this extra time to help the first AUV. But in the cooperative mode, the residual time for these 2 vehicles reduces iteratively, experiencing some fluctuations, meaning that these 2 AUVs overtaking unmonitored spots from zone 1 by 1. Again, this fluctuation refers to the sequential increment of the unexplored spots in which the residual time and the violation is calculated instantly encountering the new added spot. Well, here is a summary of the statistical analysis of the execution results for conflict-free operation and also the cooperative operation modes. This is clearly shown in this table that AUV 2 and 3 completed their operation with an excessive battery time of plus 477 seconds and plus 647 seconds, covering 100% of their allocated zone, while the first AUV only covers 47% of the area to avoid time violation. In contrast, in the cooperative operation mode, the second and third AUV respectively captured 14 and 12 additional spots from first zone, resulting in 100% coverage of the entire environment, and their residual time is reduced considerably at the mission completion. Now you can see the second AUV completed its mission with 138 seconds, which is almost nothing, and also another AUV with 78 seconds. It is also noted earlier that AUVs are resource-constrained devices and they have limited computational power and memory. So considering the total computation time in this table, it is notable that the proposed HFC algorithm is extremely fast, producing optimum solutions in the range of seconds, making this algorithm an appropriate choice for all resource-constrained vehicles, including AUVs, UAVs, USVs, and so on. Well, in conclusion, what this system can do, the proposed architecture in this research offers a truly scalable system that can adaptively increment the number of AUVs on demand without requiring any redesign or readjustment of the system parameters. In the conflict-free mode, there is no overlap among the AUV's operation. On the other hand, augmenting the architecture with cooperation operator facilitates using a minimum number of agents, considering the vastness of the environment. So in that case, for example, if in the parallel mode, we need 4 vehicles to cover the whole environment. Here you can see simply using 3 vehicles can provide 100% of coverage. Integrating the architecture with the synchronized cooperation again enables the overloaded AUV to use the idle agent's spare battery time for monitoring the unexplored areas. Again, this will help attaining unintermittent situational awareness and stable operation performance. Again, this approach is computationally fast and suitable for real-time execution on AUV's onboard processor. There are also other benefits to mention here. Modules functionality can get upgraded without manipulating the system's structure, and this increases the reusability and versatility of the system. Parallel execution of the modules speed up the computation process and make it suitable for real-time execution on resource-constrained processors. And ultimately, this design eases implementing different functionalities to be compatible with other platforms, such as unmanned, aerial, ground, or surface vehicles. Here is the reference to the published works you might want to refer if you are interested. And a full account of my publications can be found in my Google Scholar account. And I would be more than happy to establish new collaboration and extend this research area. Thank you very much for your time and attention. I would be more than happy to answer your questions.
Thank you, Dr. Sumaya, for a great and informative presentation. And now we have around 10 to 15 minutes. If there is any question, please.
Hopefully I'm not over time.
No. It was on time. Thank you.
Hello, thank you very much. Can I start with the first question?
Yes, sure, please.
Yeah, thank you. Thanks. My name is Farad, and first of all, thank you very much for the very good presentation that you did on this AUVs. It's a very promising area, and definitely in future we are going to see more and more of these applications. I'm very more interested in that sample analysis results that you presented, and there were two factors or two parameters there that got my attention. One of them was the violation, and the other one was the time of the CPU, which time of the CPU, I assume that that's the processing time that is required. If not correct, please correct me. And then about the violation, generally, what have been that parameters that you have defined in terms of the violation, and what shows that the study or that has been successful in achieving that objectives? Thank you.
Sure. Violation here is, as we mentioned earlier, the violation corresponds to the time. If, for example, for a mission, we have 1 hour, battery time is 1 hour. In a case that the operation time exceeds battery time, then we will have violation. So this is very critical for a mission, specifically for underwater operation, because we don't want a vehicle to get lost. So this is the thing. Here we define violation as the time overlap from the battery capacity. The second thing is the CPU time. Yes, the CPU time is for the simulation time. I mean, the algorithm runtime on my laptop. So it is, if you just want to implement it on a resource constraint, it will generally, you need to multiply it in 4. So again, whatever time you have here, you need to multiply it in 4 in order to implement it on a Raspberry Pi. Does it answer your question?
Yes, very good. Thank you. Thanks very much. Very clear. Thanks.
No worries.
Did you have another question or?
Hi, Maya. Can I ask a question?
Sure. Amir.
Thank you very much, Sumaya, for your very interesting presentation. So my question is about the architecture you mentioned, and how does it handle the impact of the fault if, for example, one vehicle cannot continue the mission? If you can explain briefly, I appreciate.
For sure. For example, in a case that a vehicle, for example, we define a threshold for communication. In a case that we don't hear from a vehicle in that threshold, the system considers that that vehicle is faulty. What it does, it actually the whole information from the environment, the all covered areas by the other vehicles will be communicated to the central station, or if we want to have it in a kind of decentralized computation, it will be, these information will be communicated between all vehicles. The updated environment, the covered areas, the uncovered sections, the residual time of the other vehicles will be taken into account, which is here, the fault recovery section. Then a new plan or a new mission scenario will be replanned according to using n-1 vehicles. For example, if we have 4 vehicles, one is actually discarded. The remaining time of all vehicles and the remaining spots will be reconsidered, and each vehicle will be allocated with the best order of tasks without any overlap to get to the. Possibly again, they cannot cover the whole environment depending on the size and the number of the spots, the size of environment and the size and number of spots. But again, the system tries to keep the operational performance at the near optimal level by replanning process to use the others vehicle to grab some of the uncovered areas of the faulty vehicle. Does it answer your question?
Yes, thank you very much for your comprehensive answer. And I think what I've got from your answer is that there is a replanning mechanism as well in this architecture. If any unforeseen, for example, fault happens on the system, so the system can recover this and also can replan a new mission and planning for the remaining vehicles. Am I right?
Exactly, that's true. Thank you.
Okay, thank you.
Thank you. Any more questions? If there isn't any more questions, we come to the end of this webinar. Thank you, Sumaya, for nice presentation, and thank you everyone for attending. I hope everyone stays safe and see you in our next webinar. Thank you, everyone.
Thank you.
Thank you.
Bye.
Thank you. Thanks very much.
Thank you.